Hi, and welcome to Clojure Mid-Cities Meetup Group. We go by Clojure Mid-Cities for short. I am your host tonight, John Jelinek. And tonight's going to be a really great topic. So I hope you can stick around, and I hope you'll enjoy. We're going to be talking about first principles of Clojure. Before we get started, just a few other things to run by real quick. First up, this meetup exists to help people explore the functional programming paradigm with Clojure so they can build simpler systems. And let's talk a quick agenda for the meetup. We're going to talk about a plan for 2020, and then we're going to jump right into the topic. Well, quickly, the plan for 2020 is pretty much scratch everything because we're in the middle of a pandemic, as well as unrest at the moment. So we're going to roll with the punches. But if you are available to assist in the meetup in any capacity, just hit me up on Slack. You can always go to Clojurians.net to request an invitation. We're in the Mid-Cities Meetup channel in Slack. If you caught us last time, there was an awesome talk by Eric Normand, and the publisher of his latest book that he's working on right now has graciously given us a discount code here for the book, Grokking Simplicity. So if you like 40% off, you can pop that code in on the website listed on the slide. And if you are a normal attendee here at Clojure Mid-Cities, shoot me a message, a direct message on Slack, and I've got up to 5 codes that I can give away for a free copy of the book. So hit me up if you are interested. All right, our presenter tonight is Daniel Craig. So Daniel Craig is a recent graduate from BYU Idaho, where he got a formal introduction to Lisp in the form of Emacs Lisp. He resisted Lisp then, but the Java EE developer experience has turned his heart back to Lisp and Clojure. So without further ado, I want to introduce Daniel Craig. All right, take it away, Daniel.
Hi, everybody. Thanks, John. First, I'd like to say I acknowledge that it's not any longer 5/20/2020. That date is no longer correct. Like I said in my bio, the Java developer experience has had me thinking about Clojure again. So this is actually from slides that I gave at work, and I'll say up front that it's with the intention of helping those that have never had any introduction to a Lisp to really understand the ethos of Clojure and why it's exciting to learn about. And I'll note that one thing that really put me in this vein of thinking is that, like I also mentioned in the bio that I gave John, I really did struggle at first with Clojure, with Lisp in general and eLisp. I really struggled to kind of understand why the vocabulary of functions had to be so wide. Like, why did I have to learn so many different functions to do a simple thing? And I think it's a point that, if understood, really helps you understand why Clojure in general, or in a broader sense, why Lisp. And the answer to that question is just simply that when you have those 100 functions that operate on a single data object, instead of the 10 functions that operate on 10 different data objects, then you can reason about your system in a more predictable way, and you can expect that things will act the way that they did when you last worked with them. So that's the whole idea of simplicity. That's a word that gets thrown around a lot in the Lisp community. And simplicity is something that has to be earned, as I found out. So I'd like to share this with you in the spirit of kind of stoking that beginner spirit, the fun of Clojure, the fun of the language, and hopefully you'll find something in it, if you're an experienced Clojurist or if you're an experienced Lisper, that helps you to share it with those that are around you. Something that really helps you to bring out the enthusiasm when you talk about it to others, because sometimes enthusiasm is gated by our ability to express what we love. So with that, I'll go on to my first point. So Hal Abelson presents, along with Gerald Sussman, they present structure and interpretation of computer programs. And I was struck by the first lecture that Hal Abelson gave. He basically, after the first introductory part, he gets to this question, and it's kind of the meat of his lecture. And he says, what are the most important features of a programming language? And I thought that was an interesting way to start. It almost seems too simple to start from there. But he answers the question. He says that the most important features are the primitive data types, the means of combination that it provides, and he sums that up as the question, how can I build something complex with this language? So if you have these primitive data types, what does it take to build something that's not included with the language? And then the means of abstraction that it provides. How can I build abstractions that help me to think at a higher level so I don't have to dredge through the implementation details and the decisions that I've made 6 months ago? How do I keep those from becoming decisions that I have to rethink about? So those are the 3 points that I'd like to address in this slide deck. So if at any point anybody has any questions, you can put them in the chat, and I'll break periodically, and we'll try to answer your questions. And I will go ahead and say that for myself, I don't have any professional experience in Clojure. I'm a purely enthusiastic person, but but if it comes to more battle-hardened experience, that's something that's still in front of me to earn. So I'll go on to say the primitives of Clojure are Booleans, characters, keywords, lists. It's worth noting that the Booleans are just as you expect. The characters are a little different. They start with a slash. That's just something to remember. It's honestly, they act the way you would expect otherwise. A keyword, that's like what you would use in a map. You would use it, keyword and then a value. It's a pair. And then lists, these are sort of a traditional data structure from Lisp, and they actually, as we'll see, they compose the entire structure of a Clojure program. Maps, like I mentioned, they start with a keyword. They don't have to, but most often do. And then a value that they're mapped to, each keyword. The nil type, numbers, whether floating point or fixed point, and then sets, as you see. So that starts with the pound sign, and then your curly braces and close that. So those are your primitives in Clojure. I also have 2 more to mention. So the symbols are things that they can actually be defined by users, or they can be defined in the language itself. Lisps in general don't go to a lot of effort to distinguish between things that are provided by the language and things that are defined by the user. So you'll note that I've put here plus, which is a built-in function, a symbol that's bound to a function that's provided with the language, and foo, which is sort of representative of a symbol that you could bind to an arbitrary function. And the vector is enclosed in curly brackets, and it's simply a Java vector that's been packaged to flow with the Clojure way of working. So those are your primitives. With those, you can build anything you can build in another language in terms of modeling your structures and things like that. I haven't shown anything else about procedures or anything like that. So I guess that's too broad of a statement to say that you could do anything you do in another language. That's actually yet to come. But what I mean to say is that you have this wide toolbox so that you can more complex objects and more complex structures. So before I go on, John, are there any questions? Do you know? Okay. So, oh my word.
Sorry about that, muted. All right, so Julian Sanchez asks, are string arrays of characters?
are strings arrays of characters. So that goes beyond what I know, actually.
So fortunately for you, so Michael Nygaard is in the chat, and he says strings are not arrays of characters. They are a distinct type.
Yeah. Thanks, Michael.
That's all the questions for right now.
Okay, great. Yeah, I appreciate you answering that question, Michael, and thanks everybody for understanding that this is a labor of enthusiasm, but not necessarily a labor of expertise. So, primitives are something that you work with in the language. So 3 is a primitive, 17.4 is a primitive, 5 is a primitive, and earlier we said that plus is also a primitive. So this is the second point that I'm working up to answering that Professor Abelson talked about, and that was, how do you build something complex in the language? So to build something complex in Clojure, you'll do what's called making a combination. So that's achieved by marking parentheses around your sequence. So in essence, this set of parentheses, it marks this as a combination, and it also says this is something to be executed. And it also says, in a sense, that the first thing is the function or the operator, and the remaining things are a list of operands that this operator is to be applied to. So each of those things is true, and we'll see that that's actually the basis of how you can compose these operators into more and more complex things that build on each other. So not only can you do pluses, but you can do averages, just as an example. So like I said, combinations. You're applying an operator to a list of operands. And these operands, as I mentioned, they can themselves be combinations. So you're able to do things like making a combination then be the input to another operation. So as a note, Clojure uses prefix notation. So that's why the operator always goes first. And the parentheses are not optional. It's not like mathematics where you can just add them to make something more clearly marked or more grouped, however neatly you like it. In Clojure, they mean something very specific. So that is the means of creating something complex. And it may not seem like much when you only see mathematical examples, but we'll see that in the example that I'll give after the slides, that building combinations can actually be quite a powerful thing for creating web pages. And really, like a lot of modern web development is not much more complex than this. So I'll go on. But first I'll ask if there's any questions in the chat.
No new questions yet.
Okay, great. So this slide starts with creating abstractions. So abstractions are the third thing that Professor Abelson talked about. And when he talked about abstractions, he talked about what are the means of creating abstractions so that you don't have to think about the lower layers of the design of your program. So those lower layers might be things like implementation. They might be things like representations of objects. Like, for example, if you had a fraction that you wanted to represent as a ratio so that you could have it always in a perfectly precise representation, but then when you wanted to later print it, you might want to, put it in a form that was actually in a decimal form. You might hide the details of what you implemented behind an abstraction. So def and defin are the two means of creating abstractions in Clojure. So def binds the name to a value. and specifically that value can be the result of a combination, or it can be a simple value. So this is the first example I give. It's a simple value. 5 is just bound to the name A. And because I've decided to show it as if you were typing this in the command line, I've put here this hashtag sign and then quote user /A. So that's what you'll see when you type it in the Clojure REPL. And all that's saying is that you're in the user namespace, and therefore that definition exists under this prefix user, which then protects you from getting your variables all mixed when you go into the world of building Clojure projects with different source files, because your definitions exist within the scope of where they were defined. So that goes beyond a little bit beyond what I want to talk about today. But I had that question come up once when I presented this, so I wanted to address it just in case and preempt the question if possible. So I'll go on to show an example here of how this combination can now be bound to a name. So this B is the name that I'm binding to the result of that combination. So it may not seem like much, but these are the building blocks of how you create an abstraction that lets you forget about the complexity that you're building. So define that. A, if we evaluate A, it gives us 5. If we evaluate B, it gives us the result of A times 10, which was 5 times 10, which makes 50. And then another example, you can multiply A by itself to see that 5 times 5 is 25. And then another layer removed gives you C, which is the, it's a function of A and B, which results 30. So I wanted to show all that because def, in a sense, lets you create these simple abstractions. It lets you do abstractions that don't take any parameters. They're not functions. They're just simple numbers. But that could be helpful in the example of like you're representing something as a data object, and then you want to give it a name so you don't have to think about the structure of it anymore. Later on, I'll represent a shirt as a vector that represents a collar, size, and a length. And if I name it, then I can just think of it as a shirt. Whereas if I thought of it as a vector, then I'd have to think of it as something that had a first value and a second value. And so that's the value of putting it behind an abstraction layer. Defin does the same thing, but it lets you do something like create a parameterized procedure. So where before I just had def and then a symbol name and then some simple thing, now I've got these square brackets. This is the simplest of cases, the hello world. I take no parameters and I print hello world. And if I call it, then that's what it does. But if I then provide a parameter, I'm in fact defining a procedure that teaches it how to do the square function over any number of valid inputs which take the name x. So I can provide an x1 and square 1. I can provide an x3 and square 3 and get 9. So the idea then is that I'm creating this abstraction that represents the idea of squaring. I didn't have to write a function that represented squaring 1. Instead, I have this general class of solutions that all come from the fact that I create an abstraction. So that's all very well and good. That's very basic, I'm sure, to anybody who's programmed. But I think the idea applies more generally, and that's what I hope to demonstrate in my example after the slides. So we're seeing here that I'm squaring 5, and I result 25. And I can do that on the result of the square of 5 and get 625. That's just to show that these can be composed. So what that word essentially means is that my procedure that I created resulted in something, and I can treat the procedure itself being called on a parameter in the same way that I would treat the result without any need of creating the procedure. So if I'm thinking about the square of 5, then I can think about that equivalently to the square, to the number 25 itself. And then composition says that I can, either abstract the inner part of my structure there away, the square, or I could, display it all for readability. I don't know. Depending on how you want to do it, you have a lot of flexibility because you can move your functions around because the result of them can be treated equivalently to the act of calling them. So I'll go on to show 2 more examples of abstraction. So here's one that I mentioned earlier. The average takes 2 parameters. It sums them and divides them by 2. So that's a simple average of 2 numbers. And if I do that, if I define that function, I can expect that calling it will then give me 9. So that's the magic of creating an abstraction, is just that when I want to think about the average and not think about the sum of 2 numbers divided by 2, then I have something ready-made that can save me the mental effort of diving deep into what it means to take an average. Now, an average is not a very deep dive. Everyone learns how to do an average. But when things get more complex and you can hide things behind a name, then it helps you to be able to make forward progress without having to think about the deepest levels of the logic that you're using in your program. So here's another where you take the average of 2 squares. So that would be the mean square. So between x and y, those 2 parameters that I'm providing, I square both and I take the average of them, and you can already see that I'm using this average function to then do something even more complex on these squares of 2 parameters. So you're already seeing that abstraction can help you to achieve bigger things. This mean square is bigger than average in a sense, and that's made possible because you didn't have to think about the details of what it means to take an average. So conditional logic is achieved by using this cond form. So suppose we were to take the example of the absolute value function, where if x, this value that we provide to the absolute value function, is negative, that is to say, if it's less than 0, then we invert its sign as the result of our function. And if it's equal to 0, then we provide 0 as the result of our function. And if it's greater than 0, we just return the number itself. We could define that using Clojure syntax by defining this absolute value function that takes a parameter x, and then using this form called cond, like I mentioned, and then defining each of the conditions that we want cond to consider. So you'll see that just like with the other examples, we're using prefix notation here. So this less than tests whether x is less than 0, and if that's the case, then it inverts the sign of x. And if x is equal to 0, then it provides 0 as the result of the function. And if x is greater than 0, then it provides x as the value of the function. So that, in a sense, codifies the logic that we talked about on this slide. And when I presented this once before to my coworkers, they pointed out that this is a naive implementation of the absolute value function because you really only need 2 cases. So for that in Clojure, you can actually just use the if. So I started with conditional with cond because I think that it's valuable to start with the more complex one and then let people kind of say, oh, okay, there is an if statement. It's actually easier than I thought, as opposed to the reverse where it kind of leaves people thinking like, well, that's weird. Why would you ever use cond when I have if? So just kind of a little technique. Sorry if I led you with the more confusing one. But the if one is just as you'd expect. It starts with a conditional, the less than x 0, which is readable as x is less than 0. So if that's the case, then this is the then part of the if. So I say then we invert the sign of x. Otherwise, we just return x itself. And this is a good point to point out that Clojure has no explicit return statement. This, as I was mentioning earlier, the result of a function is considered equivalent to typing a call to the function. So in a sense, when you've called a function, when you've called this absolute value function, you can think of it exactly as if the function in place where you typed it is replaced by the result that returns from it. So this x then is going to kind of replace this entire, not the definition of absolute value, but any call to it that you would make. This x sort of is returned and then finds itself in place, ready to be part of the next level of execution. It's sort of like a recursive tree sort of thing, where the depth first execution happens, and then as it sort of comes back up with results backed up to the top level of the tree, then you find yourself with broader and broader executions of functions happening on results of what were embedded method calls. So sorry if that's a little bit of an abstract thing to describe with just words, but that's kind of the way that you'll start to think as you dive into Clojure more. So those are my two examples of conditional logic. So this is the part where I'll show my example of Reagent. So I'll go ahead and pull up Emacs. So Reagent is a library that wraps React, and it's a library that is consumed by ClojureScript. ClojureScript is Clojure running in the browser, and it's Clojure that is transpiled by the Google Clojure compiler into JavaScript. So I wanted to say all that because I feel like it's important to know that, because it makes it a little bit clear how it is that you're able to bring React into Clojure and have these two seemingly disparate and at odds worlds kind of be married. And the reason I use the word married is because it's actually the same reason that I use this example at all, the example of Reagent, when talking about first principles of Clojure. And it's because I feel like Clojure, with its functional style and its composability, is really well married to Reagent, which wraps React, which is sort of built with functional principles in mind. So I enjoy making this comparison, making this example, because I think that it really demonstrates the power of the very first principles of Clojure. I really doubt that I blew anybody's mind with the slides, but you'll see that despite that, you can go pretty far with Clojure, even only knowing the first principles. So what I've done is I've just started my...
Can you make the text a little bit bigger on the...
Yeah, that's a great idea.
Great.
So I've started by bringing up the final product that I want to result at, to end at. So this is my website that I'm going to be building. It's a React app, as you can see. So it's a shirt list. It's a list of shirts that I own. Very simple example that I think demonstrates the value of the first principles of Clojure, which are the primitives and adding complexity and then abstracting your complexity away. So those three will each be demonstrated here. And I've started by showing you the final result, and then I want to wipe it away and start from fresh. So what I want to do is show you first that if I delete my my first my first method that I had there, that I'll get a compile warning. And the reason that I show this is because in eLisp, when I was doing eLisp, it wasn't always easy to get a nice compile warning. And this just says use of undeclared var, like it's so straightforward. I think that that's a huge value add for anybody who's come from eLisp. But that's not a dig at eLisp. It's a language that has its place, without saying more. So what I'll do is I'll go on to redefine this shirt website that it's complaining that I don't have. So now that I've restored that, all is restored in the world, but you're thinking, well, what's all this boilerplate that I see, and why is it that that had to be defined? Where is it being referenced? Well, like I said, to start explaining the boilerplate, like I said, all Clojure code is defined in namespaces. So at the beginning, we have a namespace that defines that this is in the Hello World CLJS namespace. So then I go on to import a couple of things. One of those is a document object model library from Google. And the next one is Reagent, which is a wrapper for React. This is left over from the fact that this is a generated template. So I'm just leaving it in. But if I was going to really customize this, I'd take it out. This is a piece of also generated code that I don't want. And now I get into the meat of it, where it's getting the div called app, where my JavaScript code is being inserted after being transpiled from Clojure. And now I've got this mount function that says, okay, well, I'm going to mount that element, which is called EL. It's been conditionally bound to this EL name, so then it's then passed here as EL. And I'm rendering my component shirt website into this thing called EL. So brushing aside all what I've just said, what you really need to know is that the shirt website component, which I'll talk more about what the word component means in just a moment, the shirt website component is being injected into a div in my index.html that says that its ID is app. And I can show you that just for sake of clarity. Public index.html. So I've got this div and its ID is app. So this is where my code is going to get pushed into. So now I've got shirt website rendering, and as you see, it's doing all of nothing. So I'd like to start to show you what the power of components is. So a component in React is something that composes your page. It makes up your page. It can be a part of another component, but it is an entity on your page that takes up space, that has colors, that has words, that has graphics, that can have state, and it's like a building block for your website. So if you're new to React, I'd recommend digging into that, because the component is a really convenient way of thinking about the structure of your app. So to go on, I'll go ahead and fill my component with a little bit more structure. So that'll take the form of typing first a div. And then, because you can't have two root level divs, I'll put another one. I'm going to put a sibling to this one in just a moment. But first, I'd like to put a title on the page. And I'll say, this is my shirt list. And that is as simple as that. Put a title on the page. So I mentioned that I'm going to put another div, and that's going to be where the list actually lives. But before I go on, I'd like to talk about that these are tags that Reagent uses to turn into the output that becomes HTML div tags. And then likewise, this H1, it functions just the way you'd expect an H1 tag to function if you were doing just boring old HTML. So I think that that's a big power multiplier for those who are learning Clojure, is that Reagent plays pretty close to, and this is due to the fact that React is the same thing, but it plays pretty close to what HTML would do. So I think that's pretty encouraging to somebody who's learning for first time to do sort of things like this. So what I'd like to do now is I'd like to define my table that defines what shirts I have, or describes what shirts I have. And I've decided that I want to call that information table. And I'm going to give it this thing called my shirts. Now, everybody knows that I haven't defined that yet, so it's clearly time for me to do something about that. The compile warning is telling me that I haven't declared my var, my shirts. So we actually need to tackle another problem first of what a shirt even means. So I'm going to make an implementation of a shirt, and you'll recall that I said that when you use def, it creates an abstraction. So my implementation of shirt is based on the vector. That's my abstraction, is that I'm calling a vector a shirt. And it'll make a little more sense when you see what I do next, because I'm not just going to use the vector functions to attack my shirt, because that would be a little bit skiwampus. Instead, I'll define these custom methods that help me to not break out of my mindset of thinking about shirts, and instead help me to think about the neck size and the length as attributes of a shirt, but without breaking out of my shirt mindset. So what you just saw that I did is one other thing that's worth mentioning, and that anybody who's done Clojure will appreciate. I can execute anything in line, and these definitions, or furthermore, these executions of simple functions that can be more complex, but just for an example, I'll give you this one, 2 + 2 makes 4. Those can all be done in line with the real-time state from your application. So even if I was to start having inputs over in this shirt list, and I wanted to have buttons that could be clicked and radio buttons and all this stuff, I could get all that state in my REPL over here in real time. Or I should say in my CIDR session, because this is what I'm using. It's called CIDR. So that's a big value add for the Clojure developer, because in essence, you don't have to then use a debugger to break down your code and to set your breakpoints and all that stuff. You can just instead test each function in line. And then, like I was saying earlier, because of the principles of composition that lets you treat a function as something that you can move around or even abstract away, then you get this cool benefit of never having to really worry too much about your functions, because they were tested really as thoroughly as can be. Now that's only true if you make them small enough to be truly simple, but that's just a pursuit of design, so I won't get too far into that. So I'll go ahead and define this getLength function, and if I'm defining it to take a shirt, and I define it that the length is considered to be the second value in the vector shirt, then that is what my definition will look like. Now I'll just bring to everyone's attention again, for anybody who is seeing vectors for the first time tonight, that this is a vector. So you'll have like this is what I'm considering to be a shirt vector, but in a broader sense, this is a vector that contains 2 strings. So that's my target right here. That's what I'm considering to be the simplest example of my data type. So I'm going to go ahead and define a shirt. I'm going to call it my favorite shirt, and I'm going to use for the first time my make shirt function, and I'm going to say that that make shirt function is going to take 2 strings. One is 16 and the other one is 33, 34. So that is comprised of my neck size and the length. So say I was to want to just run that in line, you can see that executed and showed me, okay, there's this cool new object that's called my favorite shirt. You've got it in your memory now. But say I was to just step in one right here, And I just wanted to see, well, what does it actually consist of before I define that name to be equivalent to this result of a combination. And if I wanted to just see the result of the combination without the definition, I could do the same there. And you can see that even though it's wrapped, I'm seeing the result, which is pretty cool. The vector contains 16 and 33, 34 as strings, and then that, in no abstract way, is just being simply bound to this name, my favorite shirt. So I find that that makes the developer experience pretty enjoyable, because everything you could want to know is right in front of you. So I'll just make a second shirt, and it's my second favorite shirt. I'll joke because it's a little too short, so that one is a 31, 32. Sleeves are a little bit shorter, ergo I don't like it that much. And now, to get to what we've been building up to, I'm defining a vector of shirts, which is already starting to demonstrate, our abstraction level thinking. I'm hiding vectors behind the name shirts and then building that into a vector of shirts. But I'd never had to know that the shirt was actually a vector. And by achieving that, I can do something as simple as just saying I want a vector composed of my favorite shirt and my second favorite shirt. And with no more fuss or bother, I can just define what it means when I talk about my shirts. So I see that as a big win for Clojure, because this syntax right here doesn't include the statement new anywhere. It doesn't have any parameterized data types. It doesn't have any angle brackets. It doesn't have any of that stuff, all that cruft that keeps you from just defining what you're thinking about. So I'll go on to define what an information table is. That was a mistake earlier. I didn't mean to put that colon there. But this is what I should have expected to see, which is this compile warning that says that I haven't defined what an information table is yet. So this is a good time to talk about the fact that one of the big wins for Reagent is that I'm defining React components as functions. And the fact that I can do that is pretty compelling, because React has a little bit of an interesting way of being. I am not an expert on React, but it's a stateful component that you can pass properties to. They're not parameters, but they're props, and so you kind of have to play React's game if you want them to do what you want. But in Clojure, all the syntax is just the way you'd expect. It's this tremendously consistent way of structuring the problem, where first you have the name of your component, and then you have the list of parameters that it takes, and then you have the things that it's going to do in order to result your HTML. And so you don't have to fuss and bother about all the getting the properties and all this stuff. And this is obviously the simplest case, because like I said, components can have state and all that stuff, and a function doesn't really have state that persists. So you have to then define a closure, and you can go deeper into it. But in the simplest case, I think it demonstrates this power that comes from the marriage of functional with functional, and good design principles kind of made that a happy union. So to move on, I'm defining my information table, which is a component, but you wouldn't know it because it's defined just like a function. And it takes a value called myShirts, and it then, I'm still getting information table. I'm still getting a compile error, which says use of undefined var. I think I need to refresh. Okay, yeah, that's what it was. So this is a good time to talk about the fact that I've used square brackets here, because what you would expect to use in Clojure are parentheses. Like I said, combinations are used by making parentheses. But I want to show you something, and this is just a quirk. This is a design choice that the developers of Reagent made. So I'll show you the Reagent developer console. Oh, excuse me, the React developer console. So this shirt website is a component, but you don't see this component information table. And that's because I've called it like a function. But when you're using Reagent, and only when you're using Reagent, there is this additional syntax of putting a function call or a component call inside of square brackets. And then it tells it, treat this like a component. And that's when you'll see it, that React is actually considering it as a component in itself. That's an important little got you that got me pretty good when I was trying to learn Reagent. So I point that out because I think it's valuable to know, and it's also a design choice that is important. So I'll go on to show what the rest of my app looks like, and I've only got a few more lines to go through now. But I'll start by defining a table. This table is going to be composed of rows. So I want to skip ahead and define what an information table row looks like. So this row is going to take a shirt, and it's going to simply draw this shirt as a table row. So that's what I'll do. I'll say I want a table row, and before anything else, I want it to have a cell that has a simple little character in it, just to define the start of the row. And then after that, I want to get the neck size of my shirt, and that's going to be the next cell. And then I'll do the same again when I get the length of the shirt, and that is going to compose a row, or comprise a row. That'd be a better way to say it. So I'm going to use a function called map now, where it takes a function and applies it over each element that's in a sequence. And because I have defined an information table row, what that means, and it takes a shirt, what I'm thinking is that I'll just say, okay, I want an information table row for each of my shirts that is in the list called my shirt. So, pardon me, it's actually called my shirts. So that is the result when I show you the page as it refreshes after defining what an information table row is, and then defining that I want the information table to show each of the information table rows corresponding to each of my shirts. So you didn't get to see that if I was to do something like this, then it would just simply, you know, leave out the different parts and all that. The order, you know, you can highlight different things with the way that you order things, but I skipped ahead to show you kind of my thinking and why I used map here. So I think that's an important thing to highlight, because it's a very Lispy thing to do. It's a very functional programming thing to do, to use the map function. So for anybody that's unfamiliar with that, I think it's going to be one of your big tools that you're going to come to love. And I say that from a place of the fact that I love it myself, but not from a place of professional experience. So if anybody is out there thinking like, oh, a map, like that's kind of like a beginner thing, like people don't really do that in the industry, like I'm, you know, I defer to your expertise. But for me, I think it's pretty exciting to be able to just define a function once and then, you know, map it for each value of a collection, and then simply get a updated collection with each of these results. It kind of like makes you feel more powerful than you are when you program in a language that makes you do all that explicitly. So to summarize, what I've demonstrated here is that from these simple primitives, such as vector, we can define things like shirts, which previous to this program did not exist. There was no representation of a shirt in my computer, but I was able to define one. And then I made more complex things by composing all these different, functions, just like I did, anytime you see like parentheses inside of parentheses, is essentially you're making more and more complex things. And then I defined an abstraction. And there's one final benefit of abstractions that I want to talk about, and that's that if you change the underlying implementation, then you don't effectively have to change anything else, assuming that you don't break the contract that you set out to honor in your original implementation. So just as a demonstration of that, I'll go ahead and change my implementation of the shirt, and it shouldn't change a thing. And I'll do this, from a place of wanting to demonstrate the principle, but not necessarily, not from a place of wanting to, say anything that's like mind-blowing or anything. It does seem a little weird when you see how this is done, because what I'm going to do is I'm just going to change this definition of a neck size to be nothing more than the definition first. And nothing more than the definition first. But I don't do that as a mind-blowing thing. I do it as like this is an abstraction, and when I think about it, all I was doing was giving the neck size function a shirt. So if I just define the neck size function to be the value first, which is the only thing I was doing on the shirt that I was getting in the first place, then I have in fact simplified my definition and potentially made some gains in performance or something like that. I've done it again. So in a sense, I've continued to honor that contract, that abstraction, while making some sort of desirable change that that benefited me. A simpler definition might be enough reason to change my implementation, or things like this happen all the time where you want to change the implementation of something. And if you keep nice abstraction layers between everything, then you can do it without having to rebuild the whole ant pile. So that was the takeaway that I think is most valuable, and it's the takeaway that I wanted my presentation to communicate the most, is that if you think about things like this with like a clear design head, and you build abstraction layers in between the different levels of your program, then you'll be able to avoid the collapsing effect of reaching across your different levels of implementation, and you'll end up with simpler solutions to your problems. But I think that's time for me to stop. I've run out of material. So if anybody wants to talk about any questions they have, I'd be more than happy to give it my best shot, or defer to someone else who knows better.
Yeah. All right. Well, let me pop up a question here. So Muthu Kumaran says, why did you use the, where you've got the TD stuff, why did you use parentheses for get neck size instead of these square brackets?
So the get neck size is just a simple a function that I've defined. And I didn't mean for it to be a component. So because it's not a component, it doesn't use the brackets. The brackets are kind of an exceptional thing that Reagent does to tell React, the React engine, everything that it's doing magically, that what I'm giving you is a component. So in the absence of wanting to tell it that it's a component, I can just simply use the Clojure convention of using parentheses.
Cool. And Proctor asks, how much do people use PointFree notation in Clojure generally?
Sorry, can you say it one more time?
Sure. How much do people use PointFree notation in Clojure generally?
PointFree notation.
PointFree, F-R-E-E, PointFree. So, let's see. So maybe he can be a little bit more specific. We'll see if he adds more details in the.
You're talking about like when you do like this thing where did he say free?
Yeah, free.
Okay, so that's like a macro that kind of does a little bit of Java interop, from what I understand. I haven't played in this space in the ClojureScript world, but I know that the dot has a lot to do with, new and free when you're doing Clojure, but this is beyond my experience, I'll be honest.
Sure. All right. So Proctor says not that. Okay. We'll see if he gets more, provides some more details. Okay, here we go. So Mike says using a function like def next size first is called PointFree, and that it has no parameters.
Oh, I see. Okay. Yeah, actually, I don't know. I don't know how often people use it. I watched Professor Abelson's lecture, and he did something similar to this, and I found it to be kind of like a little bit eye-opening, that you could essentially just rename a function as another thing or bind a new name to an existing function. And, in a sense, that's all it really takes to create an abstraction, is to create a name. But as far as how common it is in the Clojure users, among Clojure users, I don't know.
Yeah.
It actually isn't even originally my idea. This is something that I presented to some students of one of my former professors as I was kind of preparing for this talk. And my professor suggested it, and his background is more in Scheme and Emacs Lisp. So maybe it's an idea that comes from those languages that I sort of, without knowing, brought across a boundary or something like that.
Yeah. Mike said that the style is commonly used by people who read SICP.
Yeah.
Yeah. Cool. Yeah. So we've got about 3 minutes left. Are you able to talk a little bit about Reagent versus some of the other React wrappers?
No, I'm not. Unfortunately, I don't have any experience in any other wrapper.
Okay. Yeah. And then how easy was it to transition from using Clojure to using ClojureScript for you?
So I'll say there were some frustrations because I think the developer tools are a little bit more mature on Clojure, specifically around like Cider and InREPL, and there's a couple of things that I've had to learn more about simply because I hit walls. But I would say a big part of that is because I have Stuart Holloway's book, and so my experience learning Clojure was more guided than my experience learning ClojureScript was.
I see.
Yeah. If there was a ClojureScript book that was on my desk, I'm sure that the comparison would be much more fair.
Yeah. Yeah. Cool. And then how long did it take you to really like grasp some of these concepts and start to make something useful?
So I haven't made anything useful yet, actually, but I intend to. I have an idea that I want to build out, which is like kind of the meeting of Microsoft Excel and Oregon Trail, where you, in a sense, you use it like a financial calculator, but it also tells you the results of like, various scenarios that could happen to you. Like, say you define your goal as being that you want to be a homeowner, like you want to buy a house, and you set your budget and everything. And then it might say, okay, financial collapse could come, and you have a 20% probability of this coming, and it would take this toll on you. So like, what's your contingency? And it would sort of, in a way that's similar to the experience of a developer who's developing in Clojure, where you get this real-time feedback loop. You would get this real-time feedback loop as you developed your financial plan. So that's my goal, and it's been a learning journey. So to answer the first part of your question, you said, how long was it before I started to feel comfortable with these concepts? I think that it's been an ongoing journey, but I had a huge benefit of a formal introduction to Lisp in the form of Emacs Lisp. So that's kind of what motivated me to make this talk. And, in the humble spirit that I offer it, I hope that it helps people to take the first step of Clojure, because I think that the first principles are the most valuable ones. They're the ones that are most portable between Clojure and other languages. They're the ones that teach you the most about design. And so even if you never became a professional Clojure developer, as it sometimes, sometimes in my nightmares, I think like, oh, I never make it. I never become a Clojure developer. Even so, I can be assured that that these principles are helping me in my day job to make good design choices, to make abstractions in ways that keep me from having to rethink about my complexity. And so I would say it took me a while, but it was worth it.
Great. Awesome. Hey, thanks a lot, Daniel, for speaking today. We're out of time, but I really appreciate you taking the time to talk to our group.
Yeah, definitely. I hope that everybody was able to find something that they found valuable.
Absolutely. I know I did. Cool. Well, I'll see you soon.
Great.
All right. All right, everyone. So that is it for this month. And so once again, if you are a regular attendee of Clojure Mid-Cities, I would encourage you to reach out to me on the Clojurian Slack. And if you're the top 5 people to reach out to me, I can get you a free code for grokking simplicity from Manning. So just let me know, and we'll see you next time. Thanks a lot. Bye.